Humanoid robots emerging as the future of warfare, the U.S. accelerating AI integration into combat operations. San Francisco-based Foundation Future Industries is developing humanoid robots built specifically for military use. The company is also scaling commercial deployment across the country. In manufacturing.
Something just happened in Ukraine that is forcing the world to rethink what modern warfare looks like. 2 humanoid soldier robots have been delivered to an active battlefield for evaluation, marking a moment that many experts believe could change military history forever. The humanoid Phantom Mk1 robots were sent by the US startup Foundation, according to the company. These are not bomb disposal units. These are not remote-controlled drones. These are autonomous humanoid platforms designed specifically for combat, and they are currently being tested in real war conditions. Ukraine has increasingly become a real-world testing ground for emerging military technologies, attracting defense firms and startups from the West. But this deployment represents something fundamentally different from previous robotics experiments. For the first time, machines that walk, move, and operate like human soldiers are entering a zone where actual combat is happening. In October 2025, Foundation unveiled the Phantom Mk1, a humanoid robot designed specifically for combat and believed to be among the first built for warfare. The San Francisco-based robotics firm now plans to deploy these humanoid robots closer to the front line to refine their capabilities based on real battlefield conditions. In a recent interview with Time, Foundation co-founder Mike LeBlanc confirmed the deployment. LeBlanc said the company deployed 2 Phantom Mk1 humanoid robots to Ukraine in February. The robots were sent to the front line for reconnaissance as part of efforts to test the platform in a real combat environment. The deployment could represent the first known instance of a humanoid robot being tested on the front lines of the ongoing Russia-Ukraine war. Company co-founder Mike LeBlanc says that what he has seen in Ukraine has only strengthened his belief in the value of humanoid soldiers. He explained that humanoid soldiers could be invaluable for resupplying and conducting reconnaissance, especially in places drones cannot reach, such as bunkers. With a heat signature similar to a human's, robots like Phantom could also confuse the enemy. LeBlanc added that the aim is for the robot to be able to use any weapon that a human can use. This capability represents a significant leap from previous military robotics, which have typically been designed for specific tasks like bomb disposal or surveillance. The Phantom Mk1 itself represents cutting-edge robotics engineering. The humanoid stands about 5 feet 9 inches tall, weighs roughly 175 to 180 pounds, 79 to 82 kilograms, and is intended for tasks such as reconnaissance, bomb disposal, and other high-risk ground operations. The robot is built to operate in dangerous environments where sending human personnel may be unsafe. Potential battlefield roles include surveillance, logistics support, and handling hazardous materials during military missions. What makes the Phantom Mk1 particularly sophisticated is its technical approach. Technically, the Phantom Mk1 relies primarily on camera-based vision systems rather than complex sensor arrays like LiDAR. It also uses proprietary cycloid actuators that deliver strength, quiet operation, and backdrivability for safer human interaction. Critically, the system is designed with human-in-the-loop control. Robots manage movement and navigation, while human operators retain authority over any lethal decisions. This design philosophy addresses one of the primary ethical concerns surrounding autonomous military robots: the question of who makes life and death decisions on the battlefield. Foundation is not treating this as a small-scale experiment. Foundation is accelerating the development of military-capable humanoid robots, with plans to manufacture up to 50,000 units by the end of 2027. The company's Phantom Mk1 is designed for both industrial and defense roles, positioning it among a small group of robotic systems targeting dual-use applications. Production plans call for an initial deployment of dozens of units this year, scaling to thousands annually as manufacturing capacity expands. The company plans to lease the robots rather than sell them outright, with estimated annual leasing costs of around $100,000 per unit. Continuous operation could allow a single robot to replace multiple human work shifts in industrial settings. Phantom is currently undergoing testing at factories and shipyards from Atlanta to Singapore. The company already has research contracts totaling $24 million with the US Army, Navy, and Air Force. Tests are also planned for the US Marine Corps, during which Phantom will be trained to place explosives on doors to help troops breach buildings more safely. The company is also in close contact with the US Department of Homeland Security about the potential use of Phantom robots for patrol operations along the southern border. This suggests applications far beyond traditional military roles. But Ukraine remains the primary testing ground for combat applications. According to Ukraine state news agency United 24, the country conducted thousands of robotic operations in January alone, most focused on logistics such as delivering ammunition, weapons, and supplies to frontline troops. The Phantom Mk1 deployment builds on this existing infrastructure but represents a qualitative shift in capability. The implications of this deployment extend far beyond the current conflict. If humanoid robots prove effective in battlefield conditions, it could trigger a global arms race in autonomous military systems. Countries that master this technology early would gain significant strategic advantages. Robots do not require food, sleep, or medical care. They can operate in environments that would kill human soldiers instantly. They can be manufactured at scale once production systems are established. However, the deployment also raises profound ethical questions. The prospect of machines that can carry weapons and operate autonomously on battlefields has alarmed many experts. Even with human-in-the-loop control systems, the potential for fully autonomous lethal systems looms large. Once the technology exists and proves effective, the pressure to remove human control for speed and efficiency will intensify. Organizations advocating for restrictions on autonomous weapons have warned that developments like the Phantom Mk1 could normalize the presence of killing machines on battlefields. The concern is not just about current systems that retain human oversight, but about where the trajectory leads. If robots become standard military equipment, the path toward fully autonomous combat systems becomes almost inevitable. Military strategists see the potential differently. They argue that robots like the Phantom Mk1 could actually reduce casualties by taking on the most dangerous missions. Clearing buildings, navigating minefields, conducting reconnaissance in hostile territory, these tasks currently cost human lives. Robots that can perform these roles would allow human soldiers to stay out of the most lethal situations. The battlefield deployment in Ukraine will provide data that no simulation or controlled test can replicate. Real combat environments involve variables that cannot be predicted: chaotic terrain, unpredictable enemy actions, equipment failures under stress, and countless other factors. How the Phantom Mk1 performs under these conditions will determine whether humanoid military robots represent a genuine breakthrough or remain an expensive experiment. What is certain is that this moment represents a threshold. For the first time, humanoid robots designed for combat are operating in an active war zone. The data collected, the lessons learned, and the capabilities demonstrated will shape military robotics development for decades to come. Whether that future involves robots as battlefield support systems or fully autonomous combat platforms depends on choices that are being made right now. The Phantom Mk1 deployment is not science fiction. It is happening today, and the implications will echo far beyond the battlefields of Ukraine. China just built something that sounds impossible. A wearable robot that turns a regular person into something that moves like a centaur. The machine does not attach to your legs like normal exoskeletons. Instead, it gives you two completely separate robotic legs that walk behind you and carry the weight while you move naturally. The result is a hybrid walking system where human and machine share the work. And the numbers from testing are shocking. People wearing this system reduce their energy use by 35% while carrying heavy loads. Foot pressure dropped by 52%. The robot legs supported more than half the weight, while the person walked in a fairly normal pattern. This is not a prototype sitting in a lab. This is published research showing that humans can now walk further, carry more, and use less energy than biology allows. Researchers at the Southern University of Science and Technology in Shenzhen built this wearable robotic platform with a surprisingly simple idea. Traditional exoskeletons attach robotic joints directly to human legs, trying to amplify the power of muscles that already exist. This system takes a completely different approach. It adds two fully mechanical legs behind the user. When the person walks, the robot legs walk along with them and help carry heavy loads. The system connects to the user through an elastic interface mounted on the back. That means the robot is physically linked to the person, yet it operates as a separate pair of limbs rather than an extension of human legs. The human still controls balance and navigation, while the robotic legs handle a large portion of the weight and forward movement. The result creates a hybrid walking system where human and machine share responsibilities. The robotic legs move in sync with the wearer's walking speed and direction. Motion planning algorithms and control systems coordinate the steps so the robot remains aligned with the human stride. The researchers used model predictive control along with trajectory planning techniques to keep the movement stable even under changing walking conditions. One of the most interesting parts of the design is the elastic coupling between the human and the robot. The connection includes non-linear stiffness, meaning the behavior changes depending on the load. When the load is relatively light, the coupling stays firm, so the human and robot move together in a very coordinated way. When the load increases, the connection becomes more flexible. That flexibility allows the robotic legs to absorb forces and take over more of the load-bearing work. The numbers from the experiments are actually pretty significant. In tests, participants carried a load of about 44 pounds, which is roughly 20 kilograms. With the robotic legs assisting, metabolic energy consumption dropped by about 35% compared to walking with the same load normally. At the same time, foot pressure was reduced by about 52%. That means the system does not just make walking easier, it dramatically reduces the physical strain placed on the human body while carrying heavy equipment. During the trials, the robot legs were able to support more than half of the carried weight, while the person continued walking in a fairly natural pattern. Researchers also measured stability during movement. When people walked with heavy loads using the robotic platform, the variability in step width decreased. In other words, their walking pattern remained more stable even while carrying weight. The team believes this type of wearable robot could become useful for a range of demanding tasks. Military logistics is an obvious example where soldiers often carry extremely heavy gear over long distances. Disaster rescue operations are another scenario where responders need to move equipment across uneven terrain. Industrial environments could also benefit, especially jobs where workers transport heavy supplies repeatedly during the day. The platform redistributes vertical loads while also providing horizontal traction assistance. That means it supports the weight and helps push the user forward at the same time. The result is that people can travel longer distances with less fatigue while carrying large loads. The research describing the Centaur-style wearable robot was published in the International Journal of Robotics Research. Another development comes from researchers at the Beijing Institute for General Artificial Intelligence who introduced a new motion framework called Omni-Extreme. In their demo, a Unitary G1 humanoid robot performed a long sequence of highly athletic movements that most robots still struggle with. The robot executed breakdancing routines, martial arts kicks, forward rolls, butterfly kicks, cartwheels, alternating pistol squats, and push-ups. It even performed 5 consecutive Webster flips and finished with a rapid series of back handsprings. Some of the routines included Thomas flares and b-boy style spins that require fast contact switching with the ground. Highly dynamic movement has always been difficult for humanoid robots. Reinforcement learning is usually used to train these skills, yet once the number of movements increases, control becomes unstable. According to researcher Sang Huang, many previous demonstrations relied on overfitted tracking policies trained for one specific motion, which makes switching between different movements unreliable. Omni-Extreme approaches this differently using a 2-stage learning system. In the first stage, a unified base policy is trained using dagger-based flow matching to aggregate motion prior from multiple motion tracking experts. In the second stage, that base policy is frozen and a residual policy is optimized under strict motor constraints, domain randomization, and power safety regularization to close the gap between simulation and the real world. The result is a single algorithm capable of controlling many extreme motions instead of training separate policies for each skill. According to Big Eye, the framework achieves success rates above 90% across multiple high dynamic tasks. Researchers also conducted ablation studies to test which parts of the system matter most, measuring robot stability, movement success rate, joint energy load, and safety. The overall goal is to balance realistic motion with scalability, allowing humanoids to learn many complex skills without retraining the entire system from scratch. Meanwhile, in healthcare, researchers working on a system called Meadows have introduced a new set of intelligent dexterous gloves designed to help doctors perform delicate medical tasks with AI assistance. The gloves are part of a larger project led by a joint Stanford and Princeton research team, and the idea is to bring artificial intelligence directly into real medical procedures. Instead of AI sitting on a screen analyzing scans after the fact, Meadows is designed to work alongside clinicians while procedures are actually happening. These new intelligent gloves allow the system to assist with extremely precise hand movements, including suturing, knot tying, and handling surgical instruments. The goal is not to replace doctors. The goal is to give them an AI-powered layer of support that can help improve precision and reduce the chance of human error during complex procedures. If you found this video helpful, make sure to like, subscribe, and hit the notification bell so you never miss our latest AI and robotics updates. For more cutting-edge tech content, check out AI Tech Academy, where we break down the technology shaping tomorrow. Thanks for watching, and I will see you in the next one.